Welcome back to Diversity of Matter for Chem 30 Prep, and this lecture deals with intermolecular forces and states of matter. In your textbook it's pages 63 to 70, and this is really just a continuation off of the last lecture. So when you're looking at the examples, we're going to start at example 3, and really it's because the last lecture was just a little bit too long, so I split it in half just to make it easier to download. So by the end of this lecture, you'll be able to explain why different compounds have different melting points and boiling points. You'll be able to compare to each other. So here we'll just take a look at a molecule called difluoromethane. In terms of its structure, because I see there's a carbon here, I'm going to cheat a little bit. Carbon is almost always the center. There's 4 other atoms, so I'm just going to place those atoms around my carbon and then fill in my bonding electrons, and since fluorine needs to have 8, and this should seem right, this should seem intuitive based on the number of atoms we have there. Before we can talk about the types of bonding, we need to draw the shape diagram for this molecule, or at least understand the shape diagram. This is an AX4 molecule. It's tetrahedral, which means we have 3 atoms that are going to be in the same plane, and it doesn't matter which 3 we put in the same plane. 1 molecule coming out, and 1 molecule, or 1 atom I should say, going away. So there's a structural diagram for CH2F2, and now we're going to talk about the forces present. One force that will be present always in a molecular compound is dispersion forces, or London Dispersion, same thing. Now, because it also has polar bonds, if we take a look, CF bonds are polar. They have a fairly high difference in electronegativity. And since they're not pulling in opposite directions, they're not going to cancel out. So it's also going to have dipole-dipole forces. Now it does not have hydrogen bonding. Because the hydrogens aren't bonded to the fluorines, the only time you have hydrogen bonding is when the molecule has hydrogen bonded directly to a fluorine, or directly bonded to a nitrogen, or directly bonded to an oxygen. That's when hydrogen bonding can occur. This molecule has both fluorine and hydrogen, but they're not bonded to each other, so there's not going to be any hydrogen bonding. The charge separation for the electrons isn't as high as when it's a bond between hydrogen and one of those other molecules or atoms. Here we have another atom, or molecule, N.H and we're going to identify the types of bonding present in a sample of these molecules as well. So first we'll draw the Lewis structure, and this one's a little bit more complicated, so I'm going to list my atoms out. 2 N's, 3 H's, and a Cl, a chlorine, which means we're going to have 2 times 5 electrons, plus 3 electrons, plus 7 electrons, for 20 electrons total. And we know that nitrogen is going to be our center because it's the most electron deficient of our 3 choices. And there's 2 of them, so we'll bond them together. And then we have 3 hydrogens, so we'll start placing those, and I'll put a hydrogen there, and then a hydrogen on this side as well, a hydrogen on the bottom, and a chlorine on the bottom as well. Put in my bonding electrons, and then that's 2, 4, 6, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There we go, 20 electrons. There's our shape. If we take a look at each of our centers, we have 2 centers. Both of them are AX3E because they have 1 lone pair and 3 atoms attached to each. So we're going with trigonal, pyramidal, And for trigonal pyramidal, only 2 atoms for each center are in the same plane, so we'll do that. So we'll make the nitrogens in the same plane with each other, and then the other molecules will go towards and away. So here we have a hydrogen, here we have a chlorine, here we have a hydrogen, and here we have a hydrogen. Now when we take a look, we actually do have some hydrogen bonding here, so we can see that electronegativity wise, this nitrogen is going to be pulling on electrons from here. Chlorine is actually going to be pulling on electrons from the nitrogen, and then this nitrogen is pulling on electrons from both of our hydrogens. So we have an opportunity for hydrogen bonding off of this hydrogen, off of this hydrogen, and off of this hydrogen. So those 3 hydrogens can all do hydrogen bonding because all of them are bonded to nitrogens. So in terms of a list of forces, we also have a dipole-dipole force on the chlorine. So we actually have all 3 forces in this molecule. There's going to be London dispersion, because this is a molecular compound and it has electrons, and that's all you need to have London dispersion. It's going to have hydrogen bonding, and it's also going to have dipole-dipole forces. So if we take a look at boiling points and London dispersion forces, so these are forces, if we just take a look at the number of electrons that an atom has, and these are all noble gases, and we can see that as the number of electrons goes up, our boiling point goes up. So our boiling point continues to go up as the number of electrons goes up. And so what this means is, the more electrons you have, the more London dispersion you have, and the more energy it takes to make your atoms split apart. We can do the same thing with the halogens. If we take a look at the halogens, we know that in terms of number of electrons, iodine has the most, because it's the one lowest down in the group. So this one would have the highest London dispersion. Bromine would be second highest because this has the second most number of electrons. Chlorine has the third most, and fluorine has the fewest electrons. So in terms of boiling point, so we'll go with number of electrons. Fluorine has 9 electrons. Chlorine has 17 electrons, same as its number of protons. Bromine 35, and iodine 53. Now remember, these are diatomic molecules, so we actually have to multiply each of these numbers by 2 to find the number of electrons for each molecule. So we're actually at 18, 34, 70, and 106. So what this means is iodine should have the lowest boiling point, because it's the most electrons, the most London dispersion, and the most likely to attract other molecules to it. The attraction between iodine molecules will be relatively high compared to the attraction between fluorine molecules. And if we check our periodic table and just look at the boiling points, we can see that in the boiling point is that second number underneath the molar mass. For iodine, the boiling point is 184 degrees Celsius. For bromine, it's 59 degrees Celsius. For chlorine, it's minus 34. And for fluorine, it's actually at minus 188, which means fluorine has the weakest London dispersion of the group. Its molecules aren't that attracted to each other because it doesn't have that many electrons to begin with. They don't get unevenly distributed very often, so each fluorine molecule remains relatively unattracted to other nonpolar molecules. So if we were to take a look at the hydrogen halides, we can see the same sort of pattern happening. Hydrogen iodide has the most electrons, so it boils the soonest. As a number of molecules, or at the highest temperature, so minus 35, it's higher than minus 67. As we drop in the number of electrons, we boil sooner. It takes less energy to separate. So based on this pattern, we should say that this number should be lower than negative 84 degrees Celsius. We don't know what, and I'll never ask you for a specific temperature, but it should be lower than 84 degrees Celsius based on the idea that it has the fewest electrons in these compounds. And so since we're just changing the number of electrons, the boiling point of hydrogen fluoride should be much lower. But if we check, it's actually much, much, much higher. It takes more energy to boil hydrogen fluoride than it does to boil hydrogen iodide. And so the reason is we forgot to check our other forces. Hydrogen fluoride has hydrogen bonding. Hydrogen fluoride has an HF bond. It's very polar, which means it's attracted to other polar molecules. So if you have a sample of hydrogen fluoride, you have a sample of very polar molecules that are all attracted to each other and they stick together. So in terms of comparing force strength, we always assume that if something has hydrogen bonds, it's going to have the most attractive forces in it when compared to other intermolecular forces. After that, dipole-dipole forces are considered to be stronger than London dispersion, but weaker than hydrogen bonding. And London dispersion is the weakest intermolecular force. So if all molecules have our London dispersion, chances are they boil sooner than molecules with dipole-dipole, which are going to boil sooner than molecules with hydrogen bonding. And so just to list the forces in order, from strongest to weakest, we say hydrogen bonding is the strongest. There's hydrogen bonding, there's dipole-dipole, and finally there is London dispersion. So one more set of examples. We're going to draw the Lewis structure and VSEPR diagrams for carbon tetrachloride, bromomethane, and methanol. Before I move on, I suppose I should draw the pictures. So, if we take a look at carbon tetrachloride, a fairly easy molecule to draw. It's going to be tetrahedral. If we draw bromomethane, it's going to be another tetrahedral molecule. So C. And methanol isn't that much different. It has two centers, but really we're just replacing one of those tetrahedrals with a hydroxide group, an OH group. And so it has two centers, one's tetrahedral. This oxygen is going to be bent because it's an AX2E2. And so what we end up with is something like COH. H. This hydrogen will have coming towards us. This one will keep in the plane. And so when we do this, those are our three shape diagrams. And now we're going to compare our molecules. So we're going to compare if they have London dispersion, dipole-dipole, and hydrogen bonding. And so we're just going to flick back and forth a little bit. All of them have London dispersion forces because they all have electrons. if we take a look for dipole-dipole, this molecule has 4 hydrogens spread equally around the carbon. All of the bonds are the same because they're all CH bonds. So even if they were polar, they would cancel. They're not all that polar. The difference in electronegativity is only 0.4, but even so, they all cancel. So this molecule is definitely non-polar. If we look at bromomethane, the difference in electronegativity between carbon and bromine is actually fairly high. Carbon has an electronegativity of 2.6. Oops, sorry, 2.6. Bromine has a difference of electronegativity of, or an electronegativity of 3.0. So it's actually a difference of 0.4, which is about the same as the hydrogen-carbon bonds. But if we take a look, all the carbon-hydrogen bonds pull the electrons towards the carbon. And so what we actually have is some of the bonds cancel out, but if we take a look, this bromine is pulling away from the carbon. So there's going to be at least 2 bonds that add together in terms of polarity. So we're going to have dipole force. And you'll see that when you switch out a molecule. If you have a tetrahedral molecule and one of the atoms around the tetrahedron is different than the others, you're probably going to end up with dipole-dipole force. If we take a look at our methanol molecule, we can see that there's electrons being pulled towards this oxygen here on the carbon-oxygen bond, and this is a dipole-dipole or dipole-dipole force. There's also a carbon-oxygen bond here, which leaves an opportunity for hydrogen bonding to other molecules. So this one has all 3 forces. So we'll go back and we'll fill in our chart. In terms of dipole-dipole, nope, yes, yes. Hydrogen bonding, nope, nope, yes. And so, before I move on, what I'll say is what this probably means is that in terms of melting points and boiling points, CCl4 is going to have a lower melting point than CH3Br because CH3Br has more intermolecular forces, and that's going to have a lower boiling point than CH3OH because, again, it has more intermolecular forces. So here's some stuff you can test your metal on. In Appendix B, you can start some of the review. There's still one more lecture to go before you might be able to do all the questions, but you can definitely get a start on them, and the answers are actually in Appendix A, 10 pages before it.